We are going to talk about Treasury bonds and also about the connection between real and nominal interest rates. By the way, you see a chart from Fred. I talked about Fred earlier. And that chart illustrates the correlation between changes in the consumer price index, an approximate measure of inflation, and the interest rate for the 1-year Treasury bond. Notice that the Treasury bond interest rate is highly correlated with the inflation rate. That is especially noticeable around 1980. Let's talk a little bit more in depth about the structure of US Treasury bonds. Now, for Treasury bonds with maturities greater than 1 year, the design is as coupon bonds. A coupon bond is a bond that promises to pay a regular payment at defined intervals with possibly a final maturity payment. The reason they're called coupon bonds is because back in the old days, when bonds were paper, there would be little paper coupons that were attached to the bond, and you could tear those off in order to redeem your promised payment at the promised date. So the coupons served both as a redemption mechanism and as a record that payment had been made. Now, of course, the coupons are not physical, they're conceptual, but the essence is that when you buy a coupon bond, you are paying the market price P. In return for that market price, you are promised C, a coupon payment at regular intervals. For simplicity, let's assume it's once a year. The present value of those future payments, in theory, should equal the sum of all the coupon payments appropriately discounted plus any final maturity payment. In the equation there, P is the price you pay, C is the coupon payment, I is here assumed to be a constant interest rate, although that may not be the case. N is the number of future payments, and F is the nominal value of the final maturity payment. All of the future payments are discounted appropriately by raising to 1 plus I raised to the appropriate power. Now, in theory, for a zero risk bond, the left-hand side of that equation should equal the total value of the right-hand side. What if the interest rate does not stay constant at the value I? That's not really a problem. This basic equation can be modified to take account of expected variations in the appropriate discounting interest rate. It can be adjusted for coupon payments that are not evenly, regularly spaced out. It could be adjusted if the C does not remain constant. Because we are trying to get at the essence of the fundamental finance involved, what we're doing here is assuming the simplest possible case. Until now, everything that we've done has occurred in a world without inflation. But as we know, in the real world, there is inflation. this means we have to make a distinction about interest rates. A nominal interest rate is the interest rate that you see when you go to borrow money for a car loan. The interest rate quote you receive is what we would call a nominal interest rate. The interest you receive on a deposit with a bank or any other regular financial transaction, that's a nominal interest rate. Nominal in the sense of what you are told is that the interest rate is this. Now, when we deconstruct the nominal interest rate into its components, actually economists imagine there are two components. There's a real interest rate, small r, and an expected inflation rate, pi with a little e to indicate expected. By the way, we use pi because the letter I is already taken. So when you go to borrow money, you are paying small r, a real interest rate, a real return to the lender, and you are also paying them pi e, an adjustment factor for inflation. Now, because inflation occurs in the future, the best we can do is work with what we think inflation will be. That's why we call it expected inflation. And as a footnote, if we expect deflation, then the pi e would have a negative value. But let's not worry about deflation at this point. So think of it this way. If I asked to borrow $1,000 from you, and I offered to pay you a nominal interest rate of 10%. So after 1 year, I am promising to pay $1,100. Is that a good deal for you, the lender? Well, it depends. What if you expect that inflation will be 10%? I borrow $1,000 from you today. 1 year from now, I give you $1,100, but inflation was 10%. So in real terms, your real return would be zero. So this equation was first formulated by Irving Fisher in the early 20th century. We'll be coming back to it, but it's important to make a note that if we are dealing with a situation or a model or a scenario with inflation, we have to make it clear. Are we talking about a nominal interest rate or a real interest rate where we have subtracted out the inflation adjustment factor? See you next time.